Hi everyone, in today's class we are going to see about magnetostatics. So, myself Dr. S. Prakash, Assistant Professor EEE Department, NPRCET. So, before going into the main topics in magnetostatics, first let us discuss about the introduction of magnetostatics. So, from the name itself it indicates, as we know, when the charges are in motion it produces a magnetic force, and these magnetic force moving between free moving charges, and the study of these magnetic field along with its current is called magnetostatics. As the name itself indicates, it is dealing with the magnetic field where it is going to be a static, that is, it is not a time variant. So the next thing is we are going to list out the basic terms that are used in magnetostatics. The first one is current density. So if a charge is moved against a time t, then the current is given by I is equal to q by t. Consider a surface element ds where the current is flowing through the surface areas, and it is given by current density, and therefore current density notation is given by J is equal to di by ds. When we consider the full surface, the above equation changes as, so in the right hand side, when the ds is the denominator term of the ds is taken to the left hand side, and therefore we get di is equal to j ds, and here having the differential current, so when you take the differentiation to the right hand side it becomes integration, and therefore I is equal to surface integral j dot ds, and this is the most important equation as far as this magnetostatics is concerned. This is the current continuity equation, I is equal to surface integral j dot ds. Next we are going to see the relation between magnetic flux and magnetic flux density, and this is given by the magnetostatic Gauss law, that is surface integral b dot n cap ds is equal to phi. So where this phi is the flux and b is the magnetic flux density. So this equation is also very helpful in deriving the magnetic field for various equations. So the basic and most important law behind the concept of magnetostatics is Biot-Savart's law. So this Biot-Savart's law states that the magnetic flux density produced by the current element is directly proportional to the product of current and differential length. Current is I and dl is the differential length, and it is directly proportional to the sine of the angle between the element and line joining point theta, and it is inversely proportional to the square of the distance r between them and the point and p and the element dl, that is dh is directly proportional to I dl sine theta divided by r square. So when you take the proportionality we get some constant, dh is equal to I dl sine theta divided by 4 pi r square. So now you have the differential current element, which is a current carrying conductor, and that is carrying a current I, and that differential current element is given by di. Angle between the point P and the differential current element is given by theta. So therefore, from which now we have the formula dh is equal to I dl sine theta divided by 4 pi r square. This 4 pi r square is the constant, sorry 1 by 4 pi is the constant, and therefore if you want to find the dB, the relation between b and h is given by b is equal to mu into h. So therefore dB is equal to, just multiply the above equation by mu, that is mu I dl sine theta divided by 4 pi r square. So using this Biot-Savart's law equation, we are just going to derive the magnetic field intensity for infinite long straight conductor. That is the next topic. Now consider a straight conductor of length L carrying a current I. So now our aim is to find out the value of magnetic field intensity at any point at a distance h. So this is the diagram. So we are considering the xy plane. So the differential current element is placed on that wire. So the point P is fixed on that at a distance h. The length of the wire is L, and from the initial point to the point P the length is small l, and from the initial point to the differential current element the distance is x. So we can calculate what is L minus x. So we are using the concept of Biot-Savart law. dH is equal to I dl sine theta divided by 4 pi r square. This we know that. So also we know that B is equal to mu H. Therefore dB is equal to mu dH. Therefore we are just multiplying the mu term in dH equation. We get dB is equal to mu into IDL sin theta divided by 4 pi r square. Keep this equation as number 1. So now what we are going to do is we are going to find out dB. We are going to calculate dB. dB is equal to, take the constant outside, mu divided by 4 pi r, mu divided by 4 pi, and therefore we get the remaining term is I dx sin theta divided by r square. So now we are just going to calculate the value, same thing. So dB is equal to mu divided by 4 pi I sin theta divided by r square. From the figure we can calculate what is tan theta. Tan theta is equal to h divided by L minus x, and cot theta is equal to L minus x by h. And therefore we can calculate what is L minus x is equal to h into cot theta. Now similarly, if you differentiate the above equation, you get minus dx is equal to h is going to be the same. Cot theta, if you differentiate cot theta, we get minus cosecant square theta, and we can cancel the negative sign on both the sides, and therefore we get dx is equal to h cosecant square theta d theta. From the figure we can also calculate what is sin theta. Sin theta is equal to h divided by r, from which r is equal to h into cosecant theta. Now what we are going to do is we are going to substitute the value of dx and r in this equation number 2. So therefore we get dB is equal to mu divided by 4 pi r square, 4 pi I sin theta divided by h square cosecant square theta into h cosecant square theta. So cosecant square theta get cancelled and h gets cancelled, and leaving out dB is equal to mu I divided by 4 pi h into sin theta d theta. Now our aim is to find out the value of B. Once we find out the value of B, from that we can find out value of H. So to find the value of B, we know the value of dB. So to find the value of B, differentiation, when it is taken to the right hand side, it becomes integration, and therefore B is equal to mu I divided by 4 pi h and integration of alpha 1 to pi minus alpha 2 sin theta d theta. Next, when we integrate sin theta, we get minus cos theta. Substituting the upper and lower limit, we get B is equal to mu I divided by 4 pi h minus cos pi minus alpha 2. Minus into minus will become plus cos alpha 1. And therefore, we can write, when we rearrange this equation, B is equal to mu I divided by 4 pi h into cos alpha 1 plus cos alpha 2. Now our aim is to find out the value of h. If you want to find out the value of h, just divide the above equation by mu. Mu will get cancelled, and therefore we get I divided by 4 pi h into cos alpha 1 plus cos alpha 2. This equation 3 represents the magnetic field intensity due to finite long straight conductor. If the same case, if the conductor is of infinite long, then the alpha value becomes 0, and therefore alpha 1 and alpha 2, both the values become 0. So what the above equation will change as h is equal to I divided by 4 pi h. When we just substitute the values 0 for both the cos alpha 1 and cos alpha 2, it is cos 0 is 1. So 1 plus 1, 2. So when in the denominator 4 will get cancelled with the 2, and leaving out h is equal to I divided by 2 pi h. Now we have found out what is h. If you want to find out the value of magnetic flux density, just divide the above equation by mu. We get Bp is equal to mu I divided by 2 pi h. From the above equation, it is very clear that the value of h, it depends upon the current I and the distance h. Okay, that is, to find the value of h is equal to mu I divided by 4 pi h, the same values what we have. This is about the magnetic field intensity due to infinite long straight conductor. The same case can be, it is applicable in case of electrostatics also. We have derived the electric field intensity for finite long straight conductor and infinite long straight conductor. That is about this topic. Thank you.